Exam 4 is on Tuesday. And that is the 13th. And the topics are everything up through first law for control volumes. Normally, I have 3 office hours on Monday, 1 in the morning at the tutoring center and 2 in the afternoon. The school isn't open on Monday, so you don't have those available. So I'll try to answer emails if you send me emails. I think the best way to do it usually, by the way, it's hard to like type mathematical questions or whatever. So if you can write something down on paper and send me a picture of it, it's pretty easy to communicate that way usually. But so I'd be happy to answer any homework questions you have as long as you want to do it on stuff that's relevant to the test. Because this is sort of our last time face to face to talk about this stuff. And then, so I'll answer any questions you have. Then I'm going to finish the outline that I started last time of all the sort of topics up through what's going to be on the test. And then I'll get into a little introduction to the second law of thermodynamics. So can anybody have any homework questions? Yeah. Mm-hmm. Okay, yeah. Oh, yeah. That just has that? Yeah, sure. That's fine. Well, now that I think about it, well, on the test, everything I give you is gonna be in SI units anyways. And if so for homework, yes, that's fine. If you can find a table that just uses, yeah, that's perfectly fine. And yeah, on the test, I won't make you do any conversions or anything. Yes. Yep, you'd have to interpolate. So yeah, you would have to. Any other questions? Yes. Okay. I'll be over there in a couple minutes. Okay, first law for control volumes, part 2, and this is number 4. So a pump steadily draws water through a pipe from a reservoir at a volumetric flow rate of 20 gallons per minute. At the pipe inlet, the pressure is 14.7 pounds per inch squared. The temperature is 64 degrees Fahrenheit, and the velocity is 40 feet per second. At second point, so I'll call this the height at the inlet is 0. I'm just going to choose that as my baseline. And then at the exit, the height is 40 feet. We're going to ignore heat transfer. What's the power required for the pump? It doesn't, oh, steadily. I guess steadily means steady state. I can't imagine a pump that wouldn't be steady state. So let's start going through this equation. So dE dt is equal to Q dot minus W dot plus MI dot times the quantity HI plus VI squared over 2 plus GZI. Oh, and when I said, I'm just changing these H's to Z's so you don't get mixed up with enthalpy. And then minus ME dot times the quantity HE plus VE squared over 2 plus GZE. Okay. And we're going to assume that it's steady state. So that goes away. And these are both just equal to a mass flow rate. And we're given a volumetric flow rate. We're given a temperature. So let's use, so the temperature is, what did I say? 64 degrees Fahrenheit. So let's use the saturation table to look up what the specific volume is of liquid water at 64 degrees Fahrenheit. Okay, and we'll use that for our density, so we can go from gallons to an accurate value for mass. Okay. So anybody have the saturation table? Do you have one that's in Fahrenheit, or do we have to convert all this? That would be so great. Although that's not so hard, is it? 32, 5/9 of 32. Okay, thank you. Okay, so saturation for water. Temperature is Fahrenheit. We're at 64. Okay, so you should interpolate this. We're not going to. We're going to call this 65. Don't do this in your homework, but anyway, 65 degrees Fahrenheit. A saturated liquid has a specific volume of 0.01, so 0.01604, and that's in units of cubic feet per pound mass. And so that means that the density is equal to the reciprocal of that. So what do you get for that? 62.34, and that's pound mass over cubic feet. And then so how many cubic feet are there in a gallon? Zero 0.134 cubic feet. Okay, so we have a volumetric flow rate of 20 gallons per minute. And so the mass flow rate is equal to 20 times, 20 divided by, 20 times 0.134. And that is in cubic feet per minute. And then a minute is 60 seconds. Reciprocal of that. So 1 minute is 60 seconds. And then, so that's the volumetric flow rate in cubic feet per second. And then we have to multiply that by the density. So 62.34 pound mass per cubic feet. And so what do you get if you multiply all that out? Okay, 2.78 pound mass per second. And well, I sort of got sidetracked. So let's finish simplifying this equation. It says there's no heat transfer, I believe. Ignoring heat transfer. And it does give a velocity at the start. We're going to assume that, so, okay, it gives the velocity that the water is coming in at the inlet. We're looking for the minimum power that we need to deliver that water 40 feet high. Okay, so we're going to assume that the velocity at the exit is 0. Okay, because that's going to give us the minimum. You know what I mean? Like, if we wanted to deliver it 40 feet high at 1,000 feet per second, at a super high velocity, it would take a lot more power. So we're looking for the minimum here. So I'm going to cross that off. Okay, so Let's rewrite this equation and start putting stuff in. We have that, yeah, yep. Okay, so we have that W dot for the control volume is equal to the mass flow rate is what we calculated, 2.78. And we're multiplying that by HI minus HE. And then we are just, we're adding VI is given. That's 40 feet per second. So 800 feet squared per second squared. And then minus G, if we're doing it in feet and seconds, is 32.2. And the height is 40 feet. Okay, so the only things we have left are the two enthalpies. So hopefully we have enough to look those up. Let's see, we have the pressure and the temperature. We don't have anything telling us the pressure and the temperature at the exit. So, but with a pump, it's a reasonable assumption is that you're pulling it in at atmospheric pressure and temperature, and you're spitting it out at atmospheric pressure and temperature. So I'm gonna, in the absence of any more specific data, I'm gonna use the pressure and temperature at the inlet and the exit. And so, well, so we're going to say this and this. And since the pressure and temperature are enough to specify all the other properties, that means that there's not going to be any change in enthalpy at the beginning or the end. Okay. So HI minus HE is equal to 0. Everybody with me on that? Okay, so now I can rewrite this. The work rate is equal to 2.78 times 800 minus what's 32.2 times 40? Okay, 1296. And so what do you get if you multiply all that? Negative 1378.8. And the units would be 1288. I don't know. I'm confident you all know how to plug stuff into calculators. And so the units of energy in English units I guess is BTU, So this would be, you know, I don't know if that's the units that come out of this. Just to be careful, I'm going to, so what would that be? That would be pound mass times feet squared per second squared, and then divided by seconds. So seconds to the third. I don't know. So that's a unit of energy per second. That's just the units that we used for everything else. And then if you have to convert from that to BTU or something, you could do it. I don't work in English units really ever. So if I was doing a problem like this, I would convert everything to SI units because that's, and then go that way because that's what I'm used to doing. What? Is that what it is? Oh, that's good. It's way easier to say. Okay, does the sign make sense? So yeah, everything. So here's basically our system. So we're pulling stuff out of this reservoir. Then here's the body of the pump, and then it's lifting it up to a height of 40 feet. So our system is this, and it's plugged in somewhere, and that cord is delivering power. You know, it's delivering work into the system. Positive W or positive W dot for the first law is work being done by the system. This is work coming in, so that has to be negative. Any questions about that? That does not work. So yeah, because our system, so this thing is just sort of a black box to us, and we don't know anything like, so think about the outer surface of it. Like we have no idea what's moving, what's compressing, what's expanding, you know. We're just thinking of that as a rigid boundary. Um, so the only work that's occurring for us is just that electrical energy going in. Any other questions? Any other homework questions you want to see? Okay. Okay, so last time I started this outline of topics. And I finished talking about ideal gas law. So we're still in this section. I guess I didn't finish the section I was working on. The overall section was material properties or material relationships. Material property relationships, I think it was called. And I believe number 5 was the ideal gas law. And so now we're going on to polytropic processes. And polytropic processes are processes where this relationship holds: the pressure times the volume uh, to some exponent r is equal to a constant. Um, in almost, I mean, in every problem I can think of where we had a polytropic process, the reason that it was helpful to know that was we were going to use this to calculate pressure as a function of volume. In this case, so I'm going to call this constant C. Okay. And so pressure as a function of volume is equal to C times the volume to the negative R. And then we'd use that to calculate the work as the integral from state 1 to state 2 of CV to the negative R dV. Can't think of any cases where we've used this and not used it to calculate the work. Okay, so remember that to do that integral for the work, you have to, so it tends to be given in this form, PV to the R, but you need to get P as a function of V. If anybody has any questions about any of these, please stop me and we'll go through it. So number 7. So this is the one that's probably been most useful to us out of all of these, is the tables. And the tables, just like all those calculations, the tables are just a way to come up with relationships between material properties. And with using the tables came interpolation. And so there were 2 types of interpolation we had to do. The first one was 1D interpolation. When is it that you have to use 1D interpolation? I guess there are sort of 2 cases. The most common case that you can do a 1D interpolation is if you're at a saturation state. Because at saturation, knowing the temperature or the pressure is enough. You don't need anything else. Okay. The only other case is if you're just lucky and one of the 2 property values that you're given just falls right on one of the values in the table. Okay. So if you don't have one of those 2 cases, then you have to do the 2D interpolation. But the 1D interpolation says your f of x value is approximated as your function value at x1 plus the quantity function value at x2 minus function value at x1 divided by x2 minus x1, and then times x minus x1. Where the x's are the property that you're given, and f is the property that you want. And sometimes you have to do this. So usually your x value, the one that you're given, is temperature or pressure. But that doesn't have to be the case. There have been a couple of problems where you're given something, say you're given the specific internal energy. And then that specific internal energy that's out here in the table somewhere is what you use as your x value. And then you do it sort of like a reverse lookup, and your F is the temperature or the pressure. Okay, so it doesn't have to be that that your F is what the table is indexed by, although that's more common. And then for B is a 2D interpolation. So when you use a 2D interpolation, that would be if you're dealing with a compressed liquid that's not at saturation. Or a superheated vapor. In the case that you're not lucky with one of those values, neither of them fall on the on a value that's given in the table. And for that, you do it in 3 steps. So you'll go, the first step is you'll calculate the function. It doesn't matter what order you do this in, but calculate the function at x and y1. Calculate the function at x and y2. And then the last step is calculate the function at x and y. And each one of these is just a 1D interpolation. In this case, x and y are given, the given properties. And f is the desired property. Okay, so that's the end of the material property relationship section. So now we're moving on to the 4th overall section, and this is dealing with control volumes. So up until this point, our system was always a chosen amount of matter. Now we're dealing with a volume where matter is moving in and moving out at the instant we're looking at it. And there are two ways that we looked at control volumes. The first one is the mass flow rate balance. You can think of that also as just conservation of mass. And the equation is the rate of change of mass with respect to time in the control volume is equal to the rate of mass flow in at the inlet, or all the inlets added together, minus the rate of mass flow out at the exit. And there are two additional equations that are useful. The first one is that the mass flow rate, this can be used at the inlet or the exit, or both, is equal to the area of the opening times the speed divided by the specific volume. So this is the area of the opening the speed of the flow, and this is the specific volume. And then the second equation, that the thing that's useful pretty often, is if it's in steady state, the amount of matter inside the system is constant in time. You know, it doesn't change over time. And therefore, dm dt is equal to 0, which means that the mass flow rate in is equal to the mass flow rate out, and you can just call it all, you know. And this is the reason that, you know, when we use steady state in the first law of thermodynamics for control volumes, this is why we can make that assumption, because this is what's required for the mass in the system if you're in steady state. And then besides the mass flow rate balance, we've also looked at the first law. And the first law says dE dt for control volumes is equal to Q dot minus W dot for the control volume plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. Okay, so that's the full form. And Then we had a bunch of individual device cases. So the first one was nozzles and diffusers. And with nozzles and diffusers, we assume, so say for the most simplified form, we had steady state, what else in a nozzle or a diffuser? What can we assume? It's insulated. It's actually not the insulation as much as how fast things are going through, but yes, there's not going to be any heat transfer. So Q dot is 0. What else? That's right. It's rigid. So W dot is 0. It doesn't have any moving parts. So the boundary can't expand or contract. Okay, so there's not going to be any work done. There's not going to be any integral of PDV. Okay. And in addition to that, I mean, there's also no electricity coming in. There's no, it's not powering any moving parts or anything. So there's not going to be any work done or added. What else? What? That's right. There's not going to be any change in height that's significant. So I'll write it like that. We can eliminate both of those. And that's it, right? So that gives us that so if you combine all these, you get that HI minus HE is equal to 1/2 times the quantity V exit squared minus V inlet squared. Yes.
Kind of going off of that, when you're doing any computations with the specific enthalpy, it needs to be in times 10 to the, it needs to be in joules. You can't be working.
That's right. That's thanks for bringing that up. So in calculations where you have either potential energy effects or kinetic energy effects, most likely you're doing those calculations in SI units. Okay, like you're getting the speed in meters per second or the height in meters or whatever. And the enthalpy, if you're reading that out of a table, which you very often are, it's going to be giving that to you in kilojoules per kilogram. Okay, and so those units don't match. So if you're combining kinetic energy or potential energy calculations with enthalpy from a table, you need to re-express that enthalpy in joules. So whatever number you read out of the table, multiply that by 1,000 to put it in joules. Okay, otherwise you have a unit mismatch and everything's haywire. Okay, so that is nozzles and diffusers. And then the second one is, I don't remember what order I went before. Did I do turbines next? Okay, so turbine. And so what are we going to assume for turbines? We're going to assume steady state. We're going to assume no heat transfer. We can't assume W dot is 0 because that's what a turbine is doing, is outputting work. So do we expect W dot in a turbine to be positive or negative? We expect it to be positive, yeah. It's doing work on the surroundings. Um, and the enthalpy is going to be different at the inlet and the exit. The speed, even though the speed is going to be different, our simplified assumption, it says that kinetic energy effects are small compared to the rest of it. So change in v squared over 2, we're just going to zero that out unless you're given reason to plug that in. We're going to assume that the potential energy effects are small. So G times delta Z treated 0. And so the simplified form says W dot for the control volume is equal to M dot times enthalpy at the inlet minus the enthalpy at the exit. Okay, so what's bigger, the enthalpy at the inlet or the enthalpy at the exit? It has to be bigger at the inlet because we know W dot has to be positive, okay? And it's bigger because there's a high pressure at the inlet and a low pressure at the exit, which also corresponds to the sort of counterintuitive fact that, at least usually, the speed is faster after it's gone through the turbine than it is right before. And then, well, let's break up compressors and pumps. So let's do pumps first. So a pump is usually it usually increases the height of a liquid. We're going to assume that it's steady state. We're going to assume that there's no significant heat transfer. What about W dot? Yeah, we need that because that's the electrical power coming into the pump or the compressor. We're usually going to assume that temperature and pressure are constant, or let's say temperature at the inlet and pressure at the inlet are the same as temperature at the exit and pressure at the exit. So what does that do for us? yeah, so HI minus HE, those are the same. Or let's write it like this. So we can ignore that effect. Usually we don't care about the changes in the speed. So VI squared over 2 minus VE squared over 2. We can usually zero that out. And so we get a final form that says W dot for the control volume is equal to M dot times the quantity GZ at the inlet minus GZ at the exit. Yep.
Kind of for all of these turbine company compressor, are we gonna ever be able to use these simplified equations on their own?
I think,
Number one,
yeah. I think so. I think you should always, if you're doing calculations in a like book problem, in a problem for the class, just go through and check stuff off. I mean, for one thing, so do it step by step instead of making that assumption. For one thing, it's good practice reminding yourself what the terms mean, and I think that's really important. I think that'll help you a lot if you do that. But I think the main reason, there's sort of two main reasons to have these most simplified forms in mind. One is to sort of guide you, like when you get done with your form, you should have kind of a sense of whether that makes sense as like, is this really doing what a pump does, Like sometimes you'll forget to zero something out, and then you can kind of think like, okay, well, I don't really think that should be important, even though it's not mentioned, and then also just as far as intuition, that simplified form is a nice sort of back of the envelope type calculation to like for a sanity check on answers, or if you're doing something outside of class or whatever. But yeah, I think so. The short answer is, I think on a test or in homework, yeah, you should go through, start with the full form of the first law for control volumes and check stuff off. I think that's a better idea. So that's a pump. And then a compressor. The use of a compressor is usually to increase the pressure in a gas. And for this one, we're going to assume it's steady state. We're going to assume there's no heat transfer. Again, there's electrical work coming in, so you can't zero that out. We're going to assume that there's no significant change in height, so or that the effect of a change in height isn't going to be a big deal compared to the other things. So d times the change in z, we're just going to leave that off. And so you can write this as W dot for the control volume is equal to M dot times the quantity HI minus HE plus, the compressor. Well, sorry, I'm making this messy. So we also are not usually going to care about speed. So the change in V squared over 2, we're going to usually make that 0. And so then your final form is that W dot is equal to M dot times the quantity HI minus HE. And that is the same form as the turbine. But this time, WCV is going to be less than 0 because that's electrical power coming into the system. And so in this case, the enthalpy at the exit is going to be bigger than the enthalpy at the inlet. Okay, so that's it. That's all the stuff on the test. Anybody have any more questions about this? Okay. So now we're moving on to the next topic. And this is stuff that isn't going to be on the test. And I'm just going to give you sort of an introduction to where we're headed with the second law of thermodynamics. And the second law of thermodynamics is, excuse me, there are a couple of uses. The first one is that, like I said before, if you're using conservation laws, there's no sense of direction. You have to have other data points to figure out what happened first and what happened second. So it allows us to determine like an order of events. We haven't had that up until now. Okay, everything that we've done so far, we could run backwards and the same story would happen. And the second thing that this will let us do is evaluate the efficiency of machines, because we're going to use the second law of thermodynamics to come up with an ideal efficiency. We haven't had that up until now. There are 3 different forms of the second law of thermodynamics. So it comes in 3 different but equivalent statements. the first one is the most intuitive. This is the one that you would have known the answer to coming into this class. That's called the Clausius statement of the second law. And that says that heat will always move spontaneously from a higher temperature to a lower temperature. Okay, so that one sounds pretty obvious. You would never, even so, like when it's 0 degrees outside and it's 70 degrees inside your house, there's thermal energy outside. It's way, way, way above absolute zero, but obviously never, no matter how many times you try it, are you going to open the door to your house and have it get warmer from the winter air, I mean, there is energy out there, but that energy through heat transfer always moves from the higher temperature to the lower temperature. The surprising thing is that this is provably equivalent to, this just isn't, so this is true, but it's not super easy to see how to use this mathematically, although I guess in some cases we have used this idea. But what's important is that you can prove that this is equivalent to the two forms that you can set up as equations. Okay, so this is the most obvious. The second form is called the Kelvin-Planck statement of the second law. And this one says, instead of writing it in like a sentence form, I'm going to break it up into three things, sort of three separate keys to how this works. You can't have a process that's both, so first, a cycle. In other words, at the beginning and ending of the cycle, you're in the same state. That's what a cycle is. And second, have it in contact with a single thermal reservoir. The single thermal reservoir, you can think of that as like a heat source. Okay, so imagine that you have this, you're trying to set up this heat engine that that only has like a boiler. It just has a place where heat's coming in from a fire. That does work on the surroundings. and let's say it does net work on the surroundings. Okay, so you could hook up a heat engine to a put a fire underneath it and rig it up in a way that that it does work for a while, but it wouldn't be a cycle. In other words, the temperature of the system would have to be increasing the whole time. Okay, so it's not a cycle. The state of the system would be changing. Okay. Um, and so what this is saying is, so another way to think of this one of Kelvin statement is you can't have a heat engine where all of the energy input as heat is output as work. Okay, that's the idea. There needs to be some of that energy that comes in as heat needs to be lost as exhaust. Okay. In other words, like there's no perfectly efficient heat engine. Okay. So some of the energy that's gained as heat must be lost as exhaust. It's like a poem. There's a mathematical form of this law too. Um, Mathematically, you can think of this as for a system that's in contact with one thermal reservoir, W for the cycle, for any cycle, has to be less than or equal to 0. And so I said that these three statements are all equivalent, and you can prove that mathematically. You know, coming up with an equation like this is sort of the key to being able to do mathematical proofs with it. So there it is as a mathematical statement. So it's off the top of your head, there's no obvious reason that the Clausius and the Kelvin Planck statement are equivalent. You know, it turns out they are, but there's no obvious reason. And then the third form is the one that's going to be most important to us and the most seemingly disconnected from these, but it also turns out to be equivalent. And that's the entropy statement of the second law. So think of entropy as a measure how difficult it would be, you know, how difficult it is to use the available thermal energy as a heat engine to do work. Okay, so this is, so think of it this way. This room has, the whole room is 70 degrees, and so it has some total amount of thermal energy. Okay, there's some amount of thermal energy in this room that comes from how fast the molecules are bouncing off each other. But it's 70 degrees everywhere. Okay, so it would be impossible to use the thermal energy, and it's a huge amount of thermal energy, a shocking amount of thermal energy that's here in this room. But how easy would it be to use that energy as a heat engine? It would be impossible because it's all the same temperature. If all you have is the gas, the vapor in this room, since it's all the same temperature, you couldn't set up one thermal reservoir that's like the boiler and one separate one that's the condenser, and there'd be no way. You need those differences in temperature in order to make a heat engine, and that's connected to the Kelvin-Planck statement of the second law. Okay. On the other hand, you could have a room that had the exact same amount of total thermal energy, but half of the room was at absolute zero, and the other half was really hot, right? And then that would be a configuration where it's really easy to set up a very efficient heat engine, okay? Because all the energy over on the hot side would work for a long time to run a heat engine as the boiler versus an absolute zero side as the condenser, okay? So anyways, in order to produce a heat engine, you need your temperature zones separated as much as possible. And that doesn't say anything about what the total amount of energy is. It just says get all the energy over on this side, none over on this side, and then it's very easy to do work with that thermal energy. Okay. And if you think about it that way, you can sort of see, I think intuitively, you can kind of see how this idea, well, let me write this down and then I'll talk about it. So for any process, here's the law. The entropy for the system, the entropy in the system, plus the entropy in the surroundings is greater than or equal to zero. Okay, so that slowly that uselessness of the thermal energy creeps up. You know what I mean? It's more useful, and then a process happens, and it's less useful and less useful. At the end of the thermal death of the universe will be when everything's the same temperature and you can't make any more heat engines. And you can sort of see how that connects to the Clausius statement, right? Because imagine the most efficient configuration of thermal energy is all the energy on one side, absolute zero on the other side. So then you can run a heat engine, but as you run this heat engine, slowly the energy is trickling over. The energy that's running the heat engine is slowly moving over from the high energy side to the low energy side. And every bit of energy that moves over is less useful for running a heat engine, for getting work out of. Because now, so you move some energy over to the zero, to the absolute zero side. Now the absolute zero side is at 0.0001 Kelvin. How the hell are you going to make a heat engine where your boiler is at 0.0001 Kelvin? You know what I mean? And so that energy that's over there is basically inaccessible. And that's kind of the idea how it works. Okay, that was a lot of words, but I think everybody finds this, I find this stuff interesting. I think most people do because it feels sort of philosophical, but we're going to see how to connect that sort of philosophical idea to calculations. Okay, have a good weekend.